to represent MIT, to represent us to the world. And huge thanks to the moderator, Linda Hendry. And among her many distinctions, Linda leads Boston Globe Media as CEO, serves as a board member of The Engine, and importantly, holds a master's degree from MIT. And to all of you, it's wonderful to see you here at the start of an exciting day. This afternoon, I will be doing quite a lot of talking, so I'm going to do just very little right now. But let me say that in cooking up this program, we wanted to give all of you here, everyone watching remotely, everyone here, a taste of what it's like to be part of the MIT intellectual community. MIT has a bit more than 1,000 faculty members spread across dozens of fields. So you can consider the brilliant speakers today a kind of tasting menu to whet your appetite to the rich intellectual environment of MIT. So I hope you really enjoy. I'm looking forward to it. And let me turn it back over to Anantha.
Thank you, President Kornbluth. On behalf of faculty, students, and staff at the Institute, I want to share my warmest congratulations on your inauguration today. MIT is so fortunate and proud to have you as our president. As you have explored MIT during the past several months, it's been a pleasure to collaborate with you on various projects. One of the things that has particularly struck me has been your emphasis on inclusivity. I've seen firsthand how you're synthesizing and integrating an overwhelming amount of input from our community as you set your strategic vision and direction for MIT's future. I continue to be truly impressed by your leadership, your compassion, and your vision for the Institute. I've also been inspired by your seemingly unbounded curiosity and your passion for learning. These two qualities, which we find so important in our students, are reflected in you and are the ideas that have helped shape today's session with MIT faculty. The title of today's symposium is Where Big Ideas Come From and Why They Matter. MIT research has generated or contributed to some of the biggest ideas to ever emerge. These range from exploring the far reaches of the universe with the LIGO gravitational wave detector, to editing the genome with CRISPR technologies, to reducing poverty in developing countries through policies and programs developed by MIT's Jameel Poverty Action Lab. MIT research and inventions has had a broad impact on the world, such as the World Wide Web, RSA security, radar, 3D printing, and the list goes on and on. As our global challenge grows in number and become increasingly urgent, now more than ever, we're in need of big ideas, which faculty, students, and staff at MIT and our alumni are working hard to generate. For example, in recent years, MIT researchers have made significant advances in climate change mitigation, including decarbonization of industries, using data and science to forecast climate-related risk, advanced battery and other energy storage technologies, and removing, managing, and storing carbon dioxide, just to name a few. Ideas like these are poised to revolutionize the world, which brings us to the second half of the title, Why Big Ideas Matter. And related to this, how do we get these ideas out into the real world to make a difference? In addition to generating ideas, research teams and labs across MIT also work hard at finding ways to translate these important discoveries and breakthroughs into scalable solutions. For MIT faculty, one of the key elements of success in developing these solutions is to take an interdisciplinary approach. Problems like climate change simply cannot be solved unless researchers from nearly every discipline collaborate. Today, we'll hear about big ideas from some of our faculty who are generating them across a range of disciplines. Their talks will explore ideas in climate and energy, music, transportation, cancer research, and health. We will hear 8 back-to-back 7-minute talks and then segue into a roundtable discussion which, as President Kornbluth mentioned, will be moderated by Linda Henry, who is indeed a prominent and committed citizen of Boston and a great friend of MIT. Linda, you're truly the perfect person to moderate today's discussion about big ideas, and thank you for doing that. So before we begin, let me quickly introduce our faculty in the order they will present. First, Cullen Bui, Associate Professor of Mechanical Engineering; Andrew Lowe, Charles E. and Susan T. Harris Professor from Sloan School of Management; Ann White, Associate Provost and Associate Vice President for Research Administration and the School of Engineering Distinguished Professor of Engineering; Jinhua Zhao, Edward and Joyce Lindy, Associate Professor of City and Transportation Planning; Eran Egozi, Professor of the Practice in Music Technology, who will provide his remarks through video. Unfortunately, Professor Egozi has come down with COVID. Pablo Herrero, Cecil and Ida Green, Professor of Physics; Dina Katabi, Thuan and Nicole Pam, Professor of Electrical Engineering and Computer Science; and finally, Sangeeta Bhatia, John Jay, and Dorothy Wilson, Professor of Health Sciences and Technology and Electrical Engineering and Computer Science. I'd like to now invite Professor Bui to come on stage so we can begin. Thank you.
So excited to be here. We live in an exciting time where it is now possible to take a patient's own cells and engineer those cells using gene editing tools like CRISPR in order to eradicate their cancer or genetic diseases. As crazy as this sounds, this is not science fiction. The woman that you see on the left is Emily Whitehead. She was one of the first patients who received one of these CAR T therapies, and she has now been cancer-free for over 10 years. The woman on the right is Victoria Gray. She had sickle cell disease, and she received a therapy which consisted of her own edited stem cells, and they gave them back to her to cure her disease. Medicine cannot get more personalized than that. These amazing breakthroughs are ushering in a new frontier for medicine, but there's a challenge. Many patients will never see these solutions. Let's assume this graphic represents the total number of patients that could potentially be cured by these therapies. This number, if you look in the top left, less than 1%, is the number that will actually receive them. I ask you the question, if a cure exists, but it never gets to patients, is it really a cure? This is where my work comes in. I am passionate about developing engineering solutions that will allow these life-changing engineered cell therapies to get out into the hands and change the lives of patients. I've done this in two ways. One, through my lab at MIT, but also through a spin-out of my lab at MIT called Kytopen. Here I'm showing the team at Kytopen. Kytopen was born from the observation that a major limitation in this area is the delivery of genetic material into cells. In 2015, my co-founder Paulo Garcia and I had funding from the National Science Foundation to look at commercialization opportunities for a gene delivery technology that we were working on. As a part of this funding, we had to do customer discovery where we would interview over 100 customers and stakeholders in this space to ask them about their need for a gene delivery technology. One of the companies we met with was out in California. They were developing high-throughput synthetic biology solutions. Synthetic biology is using engineering in order to engineer cells for the benefit of mankind. During our interview with them, we asked them to take us to the place, their production facility, where all the magic happens. They take us down there, and we just see rows and rows of automated liquid handling systems that were being used for their high-throughput cell engineering. Then we asked a more specific question. How exactly are you getting the genetic material into the cell? At this point, they walk us over to a corner of the room where there were two full-time PhDs who took 96 well plates off of the automated manufacturing platform, pipetted cells back and forth, and then zapped them in order to do the gene delivery. At that moment, Paulo and I looked at each other and said, that is the problem we need to solve. Where do big ideas come from? They come from moments like this. This company had created something like a sports car for cell engineering, but it was limited to second gear because the gene delivery was too slow and too manual. Motivated by what we saw, we went back to my lab at MIT and then developed a technology that would integrate into those very same automated liquid handling systems we saw at that company. Fast forward to 2017, we had a prototype of the technology so compelling, we would present it at technical conferences and people would come up to us afterwards like, where can we buy this thing? But of course you don't buy things from MIT, you buy things from companies. Luckily for us, we ran into Reed and Katie from the Engine, and they gave us the seed funding to start Kytopen. Kytopen is poised to really revolutionize cell therapy manufacturing. But why is there a manufacturing challenge in cell therapies? A big reason is that most therapies in the clinic actually use viruses to deliver the genetic material into the cell. This brings up a big problem. If you're going to use viruses, you need two highly regulated biomanufacturing systems in order to deliver to the cells. One to create the virus, and one to put the virus into the cells. This makes the process complex, time-intensive, and expensive. Further, there's a limited amount of viral vector manufacturing capacity on the planet. Some companies have to wait up to 2 years just to get their viruses made. So you might be wondering, okay, Cullen, the problem's bad. Why are people using viruses in the first place? A big reason for this is that the original scientific discovery in many of these clinical therapies was done using viruses. People use viruses at the bench. As the name suggests, in cell therapies, the cell is the therapy. So there's a lot of hesitancy to change anything about the process as you move from the bench to the clinic to commercial manufacturing. So why does manufacturing use viruses? It's because bench scientists use viruses. Manufacturing challenges begin at discovery. So manufacturing solutions need to also begin at discovery. This is where Kytopen is really poised to have an impact in this field. We've developed a continuous flow gene delivery technology that seamlessly scales from the bench to the clinic to commercial manufacturing. When you need to engineer cells at the bench scale, it takes fractions of a second. When you need to scale up to the clinic or commercial manufacturing, it only takes a couple of minutes. The reason, we built scale-up into the physics of the system by making it continuous flow. Further, the technology is non-viral, so we can eliminate all those problems with viruses. Because of this, Kytopen is poised to revolutionize this field. We're going to first revolutionize the discovery, and that's how we will revolutionize the manufacturing. So I'm a mechanical engineer. You might be wondering, what is a mechanical engineer doing talking about these things? I'm motivated for these problems in many ways, but one of them is my son, Simeon. My son, Simeon, has sickle cell disease, just like Victoria Gray, who we showed you earlier. In sickle cell disease, one of the challenges you have is that you experience something called a pain crisis. In a pain crisis, your red blood cells form these sickle-like shapes, which get caught in your veins and arteries and cause something known as this pain crisis. There is no cure for a crisis. If you're in a crisis, all they can give you is pain medication. Adults with sickle cell disease describe a crisis as akin to having shards of glass flowing through your veins. One night, my son went into a crisis, and all I could do was hold him as he yelled out, "Daddy, help me, Daddy, help me." In that moment, there wasn't much that I can do. But the solutions we're developing at Kytopen will be able to help. But it's more than just sickle cell disease. It's cancer, it's autoimmune diseases, it's many genetic disorders. The technologies we're developing at Kytopen are going to revolutionize these spaces. It's not just about my son, it's about your mother. It's about your father. It's about your daughter. It's about anyone suffering from one of these debilitating diseases. So where do big ideas come from? They come from you, they come from me, they come from anyone who sees people like my son Simeon suffering and decides they want to do something about it. Thank you.
So I'm a financial economist at the Sloan School of Management, and I'd like to tell you a little bit about my research on applying concepts in financial engineering to accelerating biomedical innovation. So I have to begin with a disclaimer, which is I am not a biomedical expert by any means. But over the course of the last few years, having dealt with a number of friends and family with various kinds of cancer, I realized that actually finance plays a pretty big role in drug development. sometimes too big a role, in some cases creating bottlenecks and because of the wrong kind of financing or not enough financing. So that's what I've been spending some of my research time on. So I'd like to begin with an observation that biomedicine is at an inflection point. We are now able to treat all sorts of very serious illnesses with some really incredible technology. And a really good example of that is gene therapy. This is a particular treatment that's targeting single-cell mutations, typos in our DNA. And it turns out that by taking the correct version of the gene, inserting it into a virus, injecting the virus into a human patient, that virus will replace the defective gene with the correct gene, and presto, you're cured. And using this technology, we've been able to cure diseases like Leber's congenital amaurosis, a hereditary form of blindness, spinal muscular atrophy, a neuromuscular disease that causes paralysis and eventually death, certain kinds of leukemia, hemophilia, and so on and so forth. Now, many of these diseases that we've cured are fairly rare, but we are on the verge of curing some very common diseases, including sickle cell and heart disease and macular degeneration and so on. So this is a really big deal. The problem is that these cures, they don't come cheap. There are some eye-popping numbers in terms of the prices of these therapies. And although healthcare economists have established that these are actually bargains because you're getting a lifetime of health versus renting health one pill at a time, nevertheless, they're hitting healthcare budgets really hard. And so the question is, can we afford them? And this is not an academic exercise because there are over 200 gene therapies in late-stage clinical trials. So this is going to be a very big challenge in the coming months and years. So what do we do about it? Well, currently, the way these expensive therapies are being paid for is through standard healthcare plans and reinsurance. And so let me give you an example of how it might work right now. Imagine a company that's got about 1,000 employees. So this company is likely to be self-insured. They set aside a certain budget for their employees, about $6 million for a 1,000-person company. And what they're concerned about is if they even have one patient that needs a gene therapy, that could wipe out a third to a half of their annual budget. It's not sustainable. So what they want to do is to offload that risk, and they do that with reinsurance. The idea is that they pay this reinsurance company a certain premium on a monthly or quarterly basis, and in exchange, this reinsurance company will cover the cost of that therapy for that worker. The problem with this model is that currently reinsurance is way too expensive, costing upwards of 800% of the actuarial fair value of the treatment. And there are a number of structural, regulatory, and competitive reasons why that figure is not going to come down anytime soon. So it's unaffordable for a lot of these self-insured plans. And by the way, 50% of all medical spending comes from these self-insured health plans. And so what these health plans are faced with is not covering the particular therapies, lasering them out, or if they're lucky enough to get reinsurance, they have to fight with the reinsurance company that might delay or deny reimbursement because they'll tell the health plan, you should have your workers focus on cheaper therapies and see if that works first. Let's wait a year or two and see what happens. It sets up a really unfortunate dynamic where workers are pitted against employers who are pitted against these reinsurance companies. There's got to be a better way. And there is. It's called the subscription model, or more informally, the Netflix model. And let me tell you how that works. So that very same company will buy reinsurance through the Netflix model, but instead of paying for it to a reinsurance company, they will instead get reinsurance from the lowest cost provider of reinsurance. And who might that be? Who's the lowest cost provider? The answer is the drug manufacturer itself. In this example, Novartis. Because patients, they care about getting access to the therapy, not money. And so Novartis can provide reinsurance, not with dollars, but with drug. So a subscription model might work like this. The health plan would subscribe to Novartis's gene therapy by paying a certain per member per month subscription fee, maybe 10 cents per member per month. And in exchange, Novartis agrees to pay for and to administer the gene therapy for any of their patients with no additional cost. Novartis is definitely the lowest cost provider. Why? Because any other reinsurer that wants to get into the game is going to have to buy the drug from Novartis. And they're going to pay retail plus insurance markups, whereas Novartis can offer this at production cost plus a slight margin for their profit. And this particular subscription model has a number of other benefits. For one thing, this subscription model provides incentives for the health plan to diagnose and treat every single patient that needs the therapy. Why? Well, it's kind of like an all-you-can-eat buffet. Once you pay for the buffet, you're going to eat as much as you can. In contrast to the a la carte model that we have right now, where if the appetizer is a little too expensive, maybe you shouldn't do that, eat some more bread and forget about the appetizer. Second, these subscription fees, they start at approval and they get paid to these drug manufacturers in a very steady stream. And if there's one thing that Wall Street stock analysts love, it's predictable cash flows. So once these companies switch to a subscription model, their stock prices will go up because their earnings will look a lot smoother. And finally, we don't have to do this just with Novartis. We can do this with Pfizer, Spark, Bluebird. All of the gene therapy manufacturers can be included in this Netflix subscription. And this Netflix-like company can offer a menu of gene therapies to the health plans for one fee, and they'll take that fee and split it up among the various different health plans, thereby increasing efficiency, reducing the risk, and therefore the cost, and increasing access to these amazing life-saving therapies. Sounds great, right? Is it practical? Well, I'm happy to tell you that 2 years ago, I co-founded a company called Quantile Health with Yutong Sun, formerly lead data scientist at Oscar Health, so she's a consummate expert in healthcare payment systems. And as CEO, Yutong has done an amazing job. Just over the last few months, she's signed up a number of health plans for this model that covers about 4 million lives. And we're in active discussions now with various biotech and pharma companies to create a pilot program for a subscription model later this year or early next year. This is happening. So I'd like to wrap up by observing that finance doesn't always have to be a zero-sum game if we don't let it. That with the right kind of financing and the right scale and the right business model, we can actually do well by doing good, and together we can do it now. Thank you.
Good morning. It's an absolute pleasure to be here with you all today. I'm a plasma physicist, and I'm a professor in the Department of Nuclear Science and Engineering. And I'm here to talk about fusion energy, a big idea to change the world. Fusion is the power of the stars brought to Earth, where light elements combine to create heavier elements. In the stars, hydrogen to helium to carbon, all the way up to iron. As a nuclear reaction, the change in the structure of the atoms during a fusion reaction results in an enormous amount of energy released. In fact, if you could harness the energy released in fusion reactions from deuterium and tritium, you could power a city like Boston for a year with just a pickup truck load of fuel. Powering cities with small amounts of abundant fuel sourced from water and rocks. Fusion reactions do not lead to air pollution. There are no greenhouse gas emissions, no direct carbon emissions. There's minimal waste, little land usage, small environmental impact. This is the huge promise of fusion. But this promise, this tremendous value proposition, that's not the reason why fusion has been all over the news. No. The reason fusion has been all over the news is because for the first time ever, pieces of a puzzle have fallen into place. Piece number 1, community consensus and mature science. Piece number 2, policy and public-private partnership. Piece number 3, large amounts of private funding. And piece number 4, long-standing university leadership. These 4 pieces have come together to create a totally unique ecosystem, one that has accelerated the timeline to fusion energy. So this first piece of the puzzle, community consensus for a fast track to fusion electricity. There are fusion systems we know about today and work with all the time that have a very highly developed physics basis, meaning low physics risk. And the US scientific community has put forth a series of reports that chart a new mission for fusion energy within the Department of Energy. This community consensus is very special, and it has not existed before. Now, the second piece of the puzzle is policy, including a commitment to public-private partnership that aligns with science and technology goals put forth by the community. A variety of legislation supports fusion public funding and clears the path for regulated fusion power plants. And the third piece of the puzzle, private funding. There are over 38 private fusion companies now who've brought in over $4.7 billion in declared private investment in fusion. So how do these companies propose to get to fusion so fast? Many rely on a concept known as magnetic confinement. In these systems, very strong magnetic fields hold a very hot plasma, an ionized gas made up of your fusion fuel, and these plasmas are held stable for many seconds at a time so that they can be heated up to temperatures of over 150 million degrees Celsius. Under these conditions, enough fusion reactions occur each second to provide self-heating of the plasma, keeping it hot enough for more fusion reactions to occur and for more fusion energy to be released. This would be a net energy plasma, reaching a special state where fusion power produced in the plasma exceeds the external heating power. Many companies promise high performance in compact packages, and MIT alums and faculty and scientists have played key roles in founding these companies and leading them. For the fusion startup company Commonwealth Fusion Systems, or CFS, that spun out of MIT a few years back, their unique path to fusion is to build on the sound physics basis of a device known as the tokamak and leverage brand new superconducting magnet technology to build those tokamaks smaller and faster and operate them at a higher magnetic field. So this company's tokamak is called Spark. CFS was founded by Course 22 alums and faculty and scientists at MIT, and the company has caught the eye of investors. CFS raised over $2 billion, and that was $1.8 billion in Series B alone. Now, the tokamak that CFS is building is in Devens, Massachusetts. It's predicted to successfully produce net energy in the plasma core. And we make those predictions using the world's most state-of-the-art simulations, simulations that have been validated extensively against experiments by many scientific teams around the world, including students and postdocs and research scientists in my own group here at MIT. Now, the CFS device is just the first step to a fusion pilot plant, a pilot that would demonstrate electricity. Well, the company thinks that could be realized in about 15 years. Now, a second fusion company with MIT connections is called Proxima Fusion. This company spun out of the Institute for Plasma Physics in Germany, and their unique path to fusion is to build upon the physics basis of another device called a stellarator. Their innovation is not necessarily technology-driven, but it's rather about opening a door to new mathematics and computational solutions to find hidden symmetries in magnetic geometry that can lead to better particle confinement. This company has a CEO and a COO who are both alums of MIT, recent alums of Course 8 and Course 22. So the fusion ecosystem is flourishing. These pieces have fallen into place. Very realistically, we could be 15 years away from a demonstration of electricity from fusion. Fusion, a very clean, very safe, nearly unlimited source of low carbon energy. So yeah, fusion could change everything, and sooner than we think. But I still have to answer, why MIT? What role have we played in the fourth piece of that puzzle, university leadership? MIT has been a place for fusion to flourish because of MIT's investment in innovation. Big ideas don't come out of thin air. Big ideas come out of a long-standing commitment to investment in people and in their ideas. Ideas that might, just might, have a shot at changing the world. In 1958, when the nuclear science and engineering became an official department at MIT, they also established, shortly thereafter, the first fusion energy program at the Institute. And we've never looked back. The Plasma Science and Fusion Center started in 1976, and in partnership with Nuclear Science and Engineering, Course 22, and departments at MIT like Physics, Course 8, the PSFC has helped cultivate a robust graduate program in fusion energy and a really healthy and exciting undergraduate research culture. We pursued at MIT a high field path to fusion with a series of record-breaking tokamaks from the 1970s up to 2016, setting a plasma pressure record that won't be broken until a net energy device is on the scene. And in 2021, a full-scale high-temperature superconducting magnet was designed and built by Commonwealth Fusion Systems and MIT, and that demonstrated a record-breaking 20 Tesla magnetic field, the strongest fusion magnet in the world. So truly, MIT has had a fusion vision, starting over 60 years ago. A vision to hire faculty and to educate fusion students. Faculty and students who dreamt about and worked hard to bring about fusion energy. And also MIT had a vision to invest in the people and the teams, experts who help navigate sponsored research and technology transfer. At MIT, we do not follow the trends. We lead, we take risks, we make bets, we're bold. And this is just a glimpse of where this big idea came from and why we are together here today in a place where someday, maybe not too far off, we might look back and say, of course, fusion. And this is where it all began. So thank you very much.
Good morning, everyone. Throughout human history, we invented a fantastic set of technologies that help us to move from A to B. But have these technologies translated into the betterment of the mobility system? If you live in Boston, the answer is no, right? Sadly, hopefully, Boston traffic haven't treated you so badly so far, right? But Boston is not on Euro. If you look at Beijing, many of you have been to, same picture, nothing surprising. But few of you may have been to the same city in the 1980s. What do you see in the picture? Bicycles, pedestrians, public transit, by the way, electrified. What do we call this picture? In modern planning jargon, we call this sustainable travel, low carbon travel, green travel, active travel, all the beautiful vocabularies that were associated with the dreamland of transportation planning. But in the past 40 years, we have strived ourselves to move away from this paradigm. So as a profession, I think we're utterly confused. In artificial intelligence today, the most important topic is the alignment problem between machine and people. Also in transportation, we cannot align among ourselves. Let me ask you a few questions. The first one, how many people died in the road in the United States in 2021? 50,000. Very close, yeah. About 42,915 of them. Is too many? Too few? How do we judge that? Give you a benchmark. How many people died in the commercial airline industry? 0. So both in transportation, both about safety. Such a difference. Why? This is not just a conceptual question. With the autonomous vehicle coming, with the urban drones coming, with the roadside robotics coming, along the spectrum between 0 and 43,000, where do they position them? Right. Technology offers the possibilities, but social processes delineate the value trade-off. So we are working at MIT trying to define how safe is safe enough, both technologically and sociologically. Second question, many of us work in climate change. Electric vehicle is a key solution to this transportation problem. But let me ask you, who financed the US infrastructure, transportation infrastructure? The answer is gas tax. So if we are successful in electrify all the vehicles at scale, which we really hope we do, the whole tax base will go to 0. If you are the US DOT, if it's a private company, we'll be in crisis mode today, right? So at MIT, we're working with US Energy Foundation, trying to design the post-gasoline transportation financial system. And more broadly, I expect we'll see a convergence of 3 important transportation industries: car insurance company, toll road company, and gas tax collection. They may converge into one. Why? Because they all share the same trend to get more granular understanding of individual travel behavior, where you are, what time, how aggressive you drive, are you paying attention? They also share the same technology foundation, data infrastructure, sensing technology, communication platform, or computational platform. So if you're an ambitious entrepreneur, you may take on all 3 of them. Third question, this is a more personal question. What did you have for dinner last night? I really like you to think about it. What did you have for dinner last night? By the way, last night gala was so lovely. Thank you, Sally, for that. Right? No, we remember that. You had fish or beef, etc. Right? How much does that cost you? $20, $50, depending on where you are. How much time does it take you? 30 minutes or 3 hours, as we enjoyed last night? But how much carbon does that dinner embody? Most of us have no clue. We couldn't even give the order of magnitude right. So that's my first call for action. Right? We want to establish money, time, and carbon as the fundamental unit of a societal accounting. As a society, we develop a sophisticated system to track all the activities, like buying a jacket, having a dinner, driving a car, watch a movie. We know precisely how much it costs. We know precisely how much money it costs, but we do not on carbon. Right? So for that, I founded a small company called Tramda Global with 2 MIT alums, Ramiro and Ran, as a first step to account for the carbon emission in the transportation domain. So when we design for the future of mobility, I really think we should think of 3 things: changes, invariance, and human agency. What are changing in transportation? Technology, data, and value. Technology and data are obvious. MIT contribute to many of them. But I would drive our attention to values. More than solving a congestion problem today, transportation is also a climate change problem, a public health problem, and social justice problem. What's the invariance? Geometry doesn't change. Human desire doesn't change. When the cost gets cheaper, we consume more. When the cost approaches 0, we consume irresponsibly. All the transportation technology today aim to reduce travel costs. So what can we do? What can happen in 30 years? To change individual behavior is hard, particularly this type of behaviors here. But we do have instruments. There are prices, rules, and norms. Prices are the market mechanism. Rules are the laws and the policies. But I want to emphasize norms. Norms is powerful. Norm is sticky. But it can be changed. It takes about a generation to do so. I hope by bringing the behavior thinking and the computational thinking together, we can accelerate that process just enough to save our planet. MIT is a small university in the best sense of the word. Fewer boundaries, fewer conventions. University typically organize scholarship by disciplines, physics, economics, etc. But MIT also innovated, organized itself by topic or by social relevance. MIT Mobile Initiative is such an example. To answer the question, where the idea come from, I happen to teach a class called How Are Ideas Born? It's just MIT registrar doesn't allow me to use that name for the title as a class. So how are ideas born? Besides the theories, the short answer, the ideas are born when they kiss each other. Neurologically, other neurons reconnect. Biologically, it happens when genomes remix. And sociologically, it happens when people interact. MIT is such a place where ideas kiss each other. Thank you.
This is what your typical sales curve looks like for your average video game. Basically, after Christmas, no one cares anymore. But in 2005, Harmonix, the company that I started after graduating from MIT, was selling a video game. And the sales curve looked like this. It was bonkers. We'd never seen anything like it before. Every month we were selling more and more games over the previous month. That video game is called Guitar Hero. Perhaps some of you have heard of it. For those who need a refresher, the concept is pretty simple. The game comes with a plastic-shaped guitar controller. You choose a song, and then you see a series of notes coming down the screen. And you have to basically press the right button with your left hand and strum in time with your right hand. And if you do that successfully, you recreate the original guitar solo, so it feels like you're this amazing guitar player, even though you're just playing a video game. Now, I still remember in those first few months after December of 2005, being in total awe of what was going on. So first of all, we finally started making some money. Royalty checks worth millions of dollars were hitting our bank accounts. The Detroit Tigers were in the American League World Championship. And one of their star pitchers, Joey Zumaya, couldn't play because of an injury. Well, it turns out that injury was not caused because of baseball. That injury was caused because he was playing too much Guitar Hero. Guitar Hero appeared in South Park and on The Simpsons. And game critics consider Guitar Hero to be one of the most influential games in the first decade of the 21st century. But here's the thing. My friend Alex and I started Harmonix in 1995, whereas Guitar Hero came out in 2005, 10 years later. So two very reasonable questions to ask are, what made this game so successful? And what took you guys so long? So to answer that, let's go back a bit. This is me when I was 12 years old and I just started playing clarinet. So I'm one of the lucky ones. I kept playing, I love playing, and I still play to this day, and in fact I just perform quite a lot, and it's awesome. But this is unfortunately what happens to most people who try to play an instrument. The problem is that learning to play an instrument is really hard work. It takes years and years of practice. And the real problem with it is that you just sound really bad for quite a long time in the beginning. So unfortunately, the vast majority just quit after a few years. But if you can overcome this chasm, if you can get to the point where you derive real pleasure from playing your instrument, you can launch yourself into this wonderful and beautiful and satisfying world of music making. And so when Alex and I started Harmonix, we had a very clear vision for what the company should do. This was our mission statement: to let everyone in the world experience the joy of making music. And we believed in this mission statement deeply because it was very personal to us. We knew what it felt like to play a musical instrument or to make music. And we also knew how difficult it was for most people to get there. Now, As it turns out, getting from a mission statement like this to a successful product is just as difficult as learning how to play an instrument. Harmonix created no less than 10 products that you've probably never heard of in our quest to fulfill this mission statement. And the vast majority of them were commercial failures. But the thing is, with each attempt, we learned from our mistakes and we got better at what we did. We learned how to pivot and adjust, to live another day, to make another product or another game that was just a little bit better than the previous one. But the thing is, we also always kept our eye on the big goal. Even though things were not working, we just so believed that this mission statement has got to be true and that a solution has to be out there. And it was just about giving ourselves enough time to find it. And there's something else about the company, is that the vast majority of our employees were musicians. Rock bands formed in the company. In fact, our office in Central Square had, in the basement, a rock band practice room. And so there was a certain authenticity that made its way into every game that we made. And so when people started playing Guitar Hero, it felt very different than playing a regular video game. It was more inclusive. We noticed that many more women were playing our game than average. Sometimes the whole family would get together and play. And it was a game about being creative and constructive, as opposed to most video games, which are about destroying stuff. And for a number of those players, it became more than just a video game. It gave them a taste of what it must be like to be a musician, but without all those years of pain and frustration. And so as a result, many people actually went on to play a real musical instrument after playing our game. And a few years later, we started hearing stories of professional musicians who credit their professional musical life to Guitar Hero. One example is Post Malone, one of the top 10 best-selling artists of our time. His first instrument was Guitar Hero. And another is this up-and-coming guitar player who I just saw in concert the other day named Yasmin Williams. Yasmin, when she was in the middle of her set, told us that the way she got into music was because her parents got her Guitar Hero one year for Christmas. And then the following year, she begged them to get her a real guitar. And so in a bit of karmic awesomeness, to finish this off, I'm just going to play a little clip of Yasmin in concert doing a cover of a Post Malone song called Sunflower.
Thank you guys so much.
Hello, everyone. It's great to be here. Sally, congratulations. I'm an experimental physicist, and I want to tell you today about the magic of Moray quantum matter. I don't have a company, so I have to sell, these fancy names. So in my group, we're interested in the complex emergent behavior of quantum matter, okay? But what do I mean by that? So let's imagine you take a single particle, for example, a single electron, okay? Its behavior is quite simple. By that we mean that we understand it pretty well. However, if you take a whole bunch of particles interacting with each other, like many electrons, we really do not know how to calculate their properties. Their behavior is very difficult, and we do not understand it, in many cases, at all. Okay? However, many of the most fascinating states of matter in the universe are due to strong interactions between collections of particles. And this happens in all of physics and even in chemistry and biology, from the early Big Bang with the quark-gluon plasma to neutron stars when supernovae explosions happen, to very exotic states of matter in the fractional quantum Hall regime, which is a highly entangled topological state of matter. Now, I want to tell you today about a new platform that has emerged in the past few years, okay? But let me tell you first about what we have been traditionally using to try to understand these complex behaviors of quantum matter, in particular electronic systems. So the thing that we've been doing for many, many decades, okay, is just to look at actual materials, okay, with typical length scales of an angstrom or 0.1 nanometers. And the thing that happens is that these materials, once you make one, you have very limited control over what you can do with it. Yeah? And it's very difficult to change the properties, et cetera. You need to build another material if you want to look at something else. In the past 20 years, people have figured out that if you send lasers at each other, you can put atoms in very precise positions, and you can control exquisitely all the parameters of the system. And as a result, you really, we have a new platform to investigate strong interacting electrons. However, there have been, this is very difficult and very, technically very challenging, and there's only a limited set of phases and states of matter that we have been able to investigate. In the past 5 years, a new platform has emerged that we call Moiré quantum matter. Now the length scale typical is about 10 nanometers, which is about a factor of 100 from either of these other two platforms, okay? We have a lot more control than over standard quantum materials, not quite as much as the cold atoms community has, but we have been able to realize many, many phases of matter. In fact, the thing that inspired this new platform was really the wish to explore uncharted territory in quantum materials. Okay? We have been able to do this with something we call twistronics, okay? Which is the fact that you can take a material, for example, graphene. This is a single sheet of carbon atoms. And we can take now another sheet of carbon atoms, okay? And we can do something that is unprecedented in the history of materials science. We can change the angle between these two crystalline planes completely at will. So we can do this. Oops, this. Okay? We can put these two sheets on top of each other with any angle of rotation that we want. 50 degrees, 27 degrees, 1.1 degrees, why not? And this forms this Moiré pattern, which effectively works as a superstructure where new properties can be investigated. Okay? And in fact, with this new platform, Moiré quantum matter, okay, and we call it Moiré because of the Moiré pattern that forms when you superimpose these two periodic structures rotated with each other, we have been able, in just the span of a few years, we've been able to realize pretty much all of the phases of quantum matter known in nature, and quite a few new ones. Okay? We've been able to realize new correlated insulators, new types of exotic superconductors, topological phases, magnets, quasicrystals, new ferroelectrics, strange metals. The list keeps going, every month. Okay? This is something which is very unique. Let me just give you a couple of examples. Putting graphene on top of graphene, we've been able to realize the strongest superconductor in the world. Okay? This is something that happens when you put graphene sheets, 2 or more, at a very small angle on top of each other of about 1 degree. Electrons in this combined heterostructure form pairs, you can see in this picture, and the pairing glue between these two electrons is the strongest that we know. This is an experimental observation. We don't understand why it happens, but if we did, okay, there is hope that we would be able to design new, much more powerful magnets that would operate at room temperature for an immense number of applications, including better magnets for fusion technology. Another example I want to tell you is about a new type of ferroelectric materials called Moiré ferroelectrics. These are quantum devices where the interactions between electrons give you new types of ferroelectricity. Ferroelectrics are materials which are being used in investigation for energy-efficient, brain-inspired, or neuromorphic computing. And with these Moiré systems, we can realize new ferroelectrics where the polarization of the system can be changed and tuned arbitrarily, and we can realize new types of synaptic transistors, they're called, which have new functionalities which were unknown before our work. In fact, we can combine this previous superconductivity with this new ferroelectricity to make ferroelectric superconductors, something which was not available before. Yeah? Now, I want to end by emphasizing that we're doing all of this with very simple materials. Graphene is just carbon. Okay? And you can realize all of these behaviors just using carbon, for example, and also a couple of the materials where we have investigated these more structures. To some extent, you can put aside or forget a little bit of all the complexity of the periodic table, all these elements, all these rare elements which are hard to get. There's some underlying basic principles which are common to all of these states of quantum matter, and if we get to understand them and control them, we will be able to realize a new generation of quantum technologies for all kinds of applications as the types that we're hearing about today. So with this, I want to end. Thank you, Sally, and thank you all of you, and welcome to MIT.
Hello, everyone. My name is Dina Kitabi. I'm a computer scientist. So again, you're going to hear from someone who doesn't do medicine or biology about how we're going to save healthcare. Okay, but I don't have to convince you. Actually, we all know by now that the future of healthcare is data-driven, AI-powered. That is, we want to get all information, collect data about patients, their diseases, their symptoms, their response to medications all the time, use AI to create insight from that and inform healthcare. But how do we collect clinical data from patients today? We stab them with a needle, or we strap these devices on their body and try to collect data. Now, on one hand, this is not like happy experience for the patient. On the other hand, you are going to get data only occasionally, like you get one test and the next test after 6 months, 1 year, and so on. What if somebody comes and tells you, we're going to use the radio signal that is around us, that is bouncing around, to scan the brain and the body. And we're going to process that with AI to extract physiological signals like your breathing, your motor symptoms, your heartbeat, all of that stuff, even diseases. And we're going to do it all the time while the people are in their homes. So this is exactly what I'm going to show you in the next few minutes. So let me start with an illustrative video. So radio signals spread around, and they traverse walls and occlusions, and they bounce from our bodies because our bodies are made of water. And some of these signals come back to our device. Here we detect a fall and can alert the caregiver via text, email, or phone call. Now, let me show you a video with real people so that you can see that we can do this. So the big screen is what the device, what the radio device sees. And then on the side, you see what is happening inside the room. So we're going to monitor these guys through a wall because radio signal traverse walls. We're going to see how they move. So when he sits on a chair, you see he's sitting on a chair. When he stands up, you're going to see the radio signal tells us that he's standing up. When he moves with his right foot, we know that he's moving with the right foot. When he moves with the left foot, we know all of that stuff without asking people to wear sensors or to do anything differently, and through walls. And everything, of course, we compare to the gold standard to show that everything is accurate and with achieving it at very high accuracy. Now, what else can we tell? Can we tell anything about the brain? So when you go to sleep, your brain waves change, and you enter different stages: awake, light sleep, deep sleep, REM. And these sleep stages are related to diseases and, of course, sleep. But also, sleep is a platform. For example, REM, impairment in REM are related to depression. Impairment in slow waves during deep sleep are related to Alzheimer's. So how we get this today? We send someone to a sleep lab. This is from MGH. And they put these electrodes on their head and body, and they ask them to sleep like this. You can tell he's not happy. OK, let me show you what we can do. Here is our device. Transmit very low power wireless signal, 1,000 times lower power than Wi-Fi, analyzes with AI, and spits out what's called a hypnogram. For every 30 seconds, it tells you whether this person is in light sleep, deep sleep, RAM, etc. And of course, everything is compared to the gold standard, showing that it is highly accurate. So this guy is like you guys sitting, and what you see on the screen is nothing but his inhales, exhales. We asked him to hold his breath, and you see the signal stays at a steady level because he exhaled, he did not inhale. And everything is compared to the gold standard, showing high accuracy. So as we are sitting here and talking, our devices are with patients collecting data in Parkinson's, Alzheimer's, Crohn's disease, atopic dermatitis, and many others. And I want to show you that once you are able to collect such kind of data, you start changing medicine. So I want to talk about a specific disease, Parkinson's. Now, I'm sure all of you guys have heard of Parkinson's. Parkinson's actually is the fastest growing neurological disease in the world today. And a big problem in Parkinson's is that we diagnose the disease late, sometimes 10 years after the onset of the disease in the brain, because we rely on motor symptoms. We wait for the tremor and for the stiffness of motion to diagnose the disease. But by then, for some patients, 80% of the brain is already damaged. So if we want to change something, we need to diagnose Parkinson's early. We need to diagnose Parkinson's without motor symptoms. But then with what? So we went ahead and tried to read with my computer science students all the literature in medicine. We can't understand many of the things, but we understood one thing, that even James Parkinson himself, the doctor after which we call the disease, reports that breathing changes in Parkinson's. Today, no doctor can diagnose Parkinson's disease from breathing. Can AI do it? So we asked this question, can AI detect Parkinson's from nocturnal breathing? I showed you that we get breathing from wireless signals. So if we can diagnose from breathing, we also can diagnose just from the wireless signal around. So we took many nights of breathing signal. We trained a neural network to answer two questions. Does this person have Parkinson's? And if they do, what is the severity of their disease according to the gold standard? This is a large study with thousands of patients and with MGH, Mayo Clinic, University of Rochester, but let me show you the results. So if you haven't seen these curves before, the only number that you have to look at is this AUC number. You can interpret it as with 90% accuracy, we can tell from radio signals whether somebody has Parkinson's or not during their sleep, when they are not even tremoring. Now, of course, the next question, can you detect it early before a patient is diagnosed by a doctor? So that's the next question that we answer. We don't have that much data about people who are not diagnosed yet and can wait for 10 years to wait for the diagnosis. But there is a small data set that has 2 visits from people with breathing signal separated by 6 years. Okay? So let me show you whether we can take the data from the first visit and detect who 6 years later is going to report Parkinson's. So the guys who developed Parkinson's are the guys in blue, or the people in blue, and the red are the people who never reported Parkinson's. And you can see 6 years earlier, the machine learning knows those people with very high probability are going to develop Parkinson's. We have a startup that I created with my student. It's called Emerald, and it's bringing this technology to the market and enabling this data-driven, AI-powered healthcare. Thank you.
Hi there. I also want to welcome President Kornbluth to our community. The story I want to share is about how new inventions emerge from different fields coming together. At MIT, we call this convergence. I'll tell you about the fields of nanotechnology and medicine coming together to create inventions for patients with cancer. Now let's start with nanotechnology, the field of so-called tiny technologies. This is a picture of a microchip. It's a collection of integrated circuits inside each of your smartphones. You may know that the features on these chips have been miniaturized so aggressively that the nodes are smaller than 5 nanometers. That miniaturization has, of course, sped computation and made it portable. It's changed all of our lives. It has also unveiled new physics of the nanoscale. In fact, we know that if we make materials at the nanoscale, we just heard about this from Pablo, they harbor unique properties relative to their bulk counterparts. Another common example is a brick of gold. It looks golden. A nanoparticle of gold, it looks red. Now, this is a fascinating, important, fast-moving field in its own right, and it's made inspiring progress, as I've said. Now, if you're trained like me as an engineer and a physician, you wonder, what could this do for medicine? It turns out, just as these materials have unique physical properties at the nanoscale, they have unique biological properties. The way they traffic inside your body changes with their size. And that means that you can design materials that speak the language of biology. A question we've been asking is, what could these tools do for patients with cancer? Now, we know that cancer kills more patients every year than HIV, TB, and malaria combined. We know that finding it early is one of the best ways to prevent those deaths. And we also know that, just like the Parkinson's example, some cancers can quietly grow 8 to 10 years before they are detectable using screening technologies that are available today, even despite all the progress in AI and other fields. So the question we've been asking, what if we can use nanotechnology to make an ultra-sensitive sensor that could travel through your bloodstream, look for cancer, and report it to the outside world? Well, we built such a machine. Let me show you how it works. In this movie, the blue objects are 1,000 times smaller than the width of a human hair, 100 nanometers. They can circulate in the bloodstream, they leak out of blood vessels into the tumor, and they are designed to detect enzymes. The yellow objects here, these are chemicals that tumors produce in order to chew out of the tissue that they're born in and grow and spread. The way they sense is by activating a catalytic chemical reaction. So one copy makes these act like amplifiers, and it can release 1,000 chemical signals itself. Each of these is now smaller than 5 nanometers in size. And that size in the body is the size that the kidney can filter and concentrate that 5 nanometer amplified signal into the urine. So we've made an ultra-sensitive cancer detector that's completely non-invasive. We've achieved proof of concept in the lab across a wide array of tumor types. We have a startup, as many of my other colleagues here do today, that are advancing this to patients. And that is just the beginning. Like you heard from Aaron in the invention of Guitar Hero, invention is an iterative process. In fact, I imagine it's a bit like writing a song. You start in one direction, and you make it up as you go. Invention begets invention. And here at MIT, we have amazing trainees. And based on the foundation that I showed you, they've been asking questions about how we could do more. What if you could make the urine test better? Instead of sending it off to screening for the lab, what if we could make it like a pregnancy test on paper? This is a publication that came out yesterday. What if you were screening for lung cancer? Could we make a breathalyzer that gives you a signal in 10 minutes? And what if, once there was a positive test, we could make the nanoparticles into imaging agents that could help us visualize whether tumors have spread? What if you could make the nanoparticles carry therapeutic payloads? And on and on and on. Nanotechnology can unlock a whole new paradigm in cancer research. So, how does MIT nurture this kind of convergence? What is so special here. Along with all of the technologies you've seen, MIT as its core is made up of curious people, and we exist in nested communities. Here's the core of our nanomedicine community in the Marble Center. We are 6 faculty, we represent 200 researchers, we like and we trust each other. We live together in the Koch Institute for Cancer Research, which is an entire building of 1,000 researchers in 30 labs, and it is structurally built so every floor is half engineers and half biologists who interact. And if you zoom out and look at where we are in the middle of Kendall Square, in the middle of this community of pharma, of venture, of startup incubators, you can see that these nested communities are designed to have an enormous collective impact. The impacts for this community can be measured in many ways: trainees, inventions, publications, patents. Here's just one more: startups. Over the last 15 years, this community of investigators in the Koch Institute has founded 130 startups to advance their inventions to patients. Now, I want to leave you with a concrete image of what this convergence actually looks like. It's not just the collision of nanotechnology and cancer research, but artificial intelligence and stem cell biology and genomics and robotics and wearables. It's a big, beautiful mess. And it's accelerating us into a better future for cancer patients and beyond. One where we hope to intercept cancer while it is curable, harness the immune system to help us treat cancer, and make diagnostics and therapies available for patients not just here, but around the world. That is the unbounded future we are dreaming about. Thank you.
That was incredible. Thank you all so much. I'd like to start with a round of applause for our incredible speakers this morning. You know, we live in an era of where innovation is just sort of connected and so important to what we do. We're obsessed with it. Every company has an innovation and chief innovation officer. And we are facing global challenges now that demand humanity's best and broadest thinking now more than ever. And there have been some people who have been saying, would argue that the flow of new ideas is drying up. And I would say that those people have not had breakfast on Monday morning at MIT. So you've heard in each of these presentations that these aren't ivory tower concepts. This is the future being built here, right here on this campus and beyond. And what a time to be alive. These panelists give us so much hope for a better tomorrow for so many. And while this is an inspiring time in terms of innovation, this is also a really complicated time here and abroad. I work at a newspaper, and this is really a lot of what we're telling the story of every day. And now more than ever, we need leaders who are willing to make decisions based on science and data and see what comes out of that happy combination, and introduce policies that prioritize the health and well-being of our communities, our people, and our planet. We need leaders that can bring diverse perspectives and voices to the table to tackle complex challenges and create a more just and equitable future. In short, we need a little more MIT in a lot of places. And Dr. Kornbluth is up to that task. And I congratulate the whole MIT Corporation on the successful and comprehensive process that brought in this inspired leader. Round for. Dr. Kornbluth has shown throughout her career that she is a visionary and inclusive leader who understands how to work with people, science, and technology to transform the world. I look forward to seeing her steer MIT at this exciting new chapter that we're all here for, one where science and innovation are used to improve lives here and around the globe. So now I get to this incredible all-star panel. I'm going to start with questions one by one for each of you, and then we'll open up to a broader discussion. And Cullen, I want to start with you. The cell engineering innovations you described have incredible potential for curing disease through genetic engineering. Can you talk about barriers or limitations that exist that you're working on?
Yeah, I think one of the big challenges that we face is patience. Will the community and the world be patient enough for these technologies? So, there's a lot of interest and excitement in the therapeutic solutions, and there's a lot of economic potential of those. But what about the infrastructure, the things that our company's working on, but there's a lot of people working in this space. Will there be enough patience to continue to invest and continue to wait for that return? Because it's not a 5 to 7 year type of thing. It's more like 10 to 20 years. And so, will the field have enough patience to wait for the infrastructure to be built to enable these new systems?
I thought you were first saying patience, as in
no.
people needing the treatment.
We need patience for patience.
And that's one of the things that's so remarkable, is that you are working so far in the future. Is there anything that you're working on that's nearer term?
There are some things. I think one of the things we're also looking at, I talked a lot about engineering human cells, but we're doing a lot of stuff with bacteria as well, which is something that I've been fascinated by. Actually, the company, when it was founded, it was originally going to look at bacteria and then pivoted to human cells. So my lab at MIT has developed some interesting parallel technologies that are allowing us to do really fast genetic engineering in bacteria and microbes, which have implications for clean energy, novel, sustainable materials. So actually maybe even broader than the healthcare things.
Wow. Well, I know some people you might want to talk to about that. So Andrew, there are a lot of organizations that do self-insure, and you do have that moment where somebody gets sick and it's sort of that crisis moment. So what you were describing was a real and practical need that so many organizations face. Are there other applications and novel financing methods that you can see outside of healthcare?
Well, absolutely. So about 7 or 8 years ago, I was invited to give a talk by Dennis White, the head of the MIT Plasma Science and Fusion Center. And I was a bit surprised, but didn't know anything about fusion, but was quite excited to learn more about it. And we were talking about the ways we can make fusion a reality by better financing. And so, to someone with a hammer, everything looks like a nail and, guilty as charged. And so when I looked at the landscape of fusion, what I saw was a portfolio of intellectual property. I mean, obviously, you need to achieve a certain set of criteria to get fusion to work, to ignite the plasma. But along the way, there are probably 25 or 30 different technologies that need to be developed, engineering problems that need to be solved. That's a portfolio that can be invested in. And so Dennis and I worked on a paper to describe that portfolio. Some of those ideas were the basis of Commonwealth Fusion Systems. And given the breakthroughs that Professor White talked about in fusion over the last 24 months, we're seeing the possibility of applying some of those portfolio principles on a much larger scale. So we're working on that as we speak.
And so that's something, how far in the future are you talking?
I'm talking 3 to 5 years. Because while it may take 15 years to achieve fusion, it's going to be a lot quicker to develop a number of those technologies. Like superconducting magnets, it's going to have applicability to all sorts of areas and industries. So I think nearer term investment opportunities are really attractive. And of course, if we ever achieve fusion, which obviously many people have agreed that we now can and we have, the fact is that there's energy transition that's going to happen. That's a whole nother set of investments. So this is a really exciting time for this field.
It's really exciting, and I appreciate the thoughtfulness that Dinanatha had in terms of putting together this panel to see all of the different ways that innovation and curiosity can take us and how it's shaping our future. So I was especially excited about that. And speaking of fusion, the World Commonwealth Fusion that's here in Massachusetts, it is so exciting. You mentioned in your presentation that it was 15 years. Can you talk to us what needs to happen in that 15 years and sort of your best estimates?
Sure, absolutely. It's a really good question. And so we think in our department about science, systems, and society when we think about how to get to these kinds of aggressive timescales for something like fusion. And Andrew, thank you. You already talked about some of the financial systems behind it and societal connections. So I'll mention something about science and a little more on the engineering systems. One thing that we're going to need to do as a community to bridge between where we are today and where we need to be is to think about materials materials that are going to take us from being able to operate a fusion device for, 4 or 5 days a week, 3 months a year, in an experimental mode where scientists like me go and take data and study it, bridging from that to where we're going to be operating a electricity-producing power plant. Right? That is going to have to operate, 24/7, many, many months of the year for many, many years. So materials are a big part of that. What kind of materials can we use to handle heat? What kind of materials help us exhaust the heat? What are the right materials to help us convert the energy from fusion reactions into electricity? And so there's a lot of really exciting things happening right here on campus, again at the Plasma Science and Fusion Center, thinking about innovations in, for example, molten salt blankets that we would use to convert the kinetic energy of a neutron, help us convert that kinetic energy into heat, which we then use to produce electricity. These are the types of things that folks are working on, and they're looking at different technologies for these materials, different options for these materials at a variety of technology readiness levels. So you've got some that are really ready to go. Maybe that's some of the IP, in a 3-year, 5-year timescale, and some that are a little farther out that we want to develop more on that, decadal timescale.
Fascinating. Jinhua, your research on the future of transportation is really exciting, and I think that one of the things that I got out of your presentation is that when we're talking about driverless cars, we're asking the wrong question, because there are all these programs. Well, what do you program a car to do to make a decision between if hitting a child or hitting, another car, or what those decision makings? What should we be looking for in the future of transportation here in the U.S.?
Thank you. First of all, I just came back from Barcelona last week, right? I would say that for anyone who claims work on transportation cities, should live in Barcelona for 3 months before seeing anything, right? It just offers different imagination what city could look like, right? Compared to we do this quantum mechanics, these fusions, the healthcare, etc. U.S. lead the world in many aspects, but sadly, transportation we don't. So I think we need the degree of humility here, right? There are many parts of the world are experimenting, are leading in better models. I think we should go and learn from them. So that's the first thing I would say. The second one is really we need to come together and be clear on what do we mean by success. As I showed you the initial picture, I think that we don't have a consensus on this, right? If you continue to define success as the number of cars we pass through the highways, I don't think we'll ever reach a good result here, right? So even within MIT, actually, there are 2 contrasting schools of thought on how do we manage cities. One school says, let's treat cities as just machines. If only we sense everything, we measure everything, we predict everything, optimize everything, we solve the problem. It's a gigantic machine, right? But the other school of thought saying, no, cities are messy, cities are chaotic. We don't want to just optimize all the time. We want the ad hocness. For a long time, I thought the two are never going to reconcile with each other, right? Just like MIT, all the debates we had. But now I actually come to a view that they indeed could be complementary in the sense that only certain component of the system, namely car, is structured and controlled. The other part of the system, namely pedestrian, can really enjoy the freedom here.
Interesting. I had a visual of Pablo's interacting cells when you were describing the city and the chaos. So, Pablo, you are a physical scientist and you're focused on basic research of quantum matter. Can you talk about the importance of basic research and discovery in these innovations?
Yeah, so I really want to throw a pitch for basic research. I think many of the innovations that my colleagues have spoken about originally stemmed from scientists who were doing pure research without having these innovations in mind. And there are many, many, many examples. One of them that I like to point out, for example, is Einstein's theory of relativity. Initially very obscure mathematics, which people thought, well, this may never be applied for anything. Turns out our GPS satellites include corrections of relativity that allow us to know where we are with about a centimeter accuracy. If they weren't there, we wouldn't know where we are within about 10 kilometers. So things that can take many years, many more than 15 years. 15 years for me is like short-term horizon. When the first transistors were invented, it took them about 40 to 50 years until they revolutionized computing. So I think that it's important to invest in basic curiosity. You're just motivated by something, to understand something, and then often the most dramatic revolutions in technology happen from that curiosity-initiated research.
I love that, and that's ties in so well to the theme of this curiosity unbounded, that following where the curiosity takes you, which I know is President Kornbluth's one of our major themes for this. Dina, so you presented a really fascinating technology about these wireless sensors. What are possible additional applications for this technology, and what is the timeline before we're able to put this and really deploy this in people's houses?
So let me answer the second part first, because as we are speaking, we have devices that are monitoring patients with Parkinson's, with Alzheimer's, with Crohn's, with atopic dermatitis, kids, older people across all ages. So they are in patients' homes, and they are collecting amazing amount of data that enabled us, like the Parkinson's stuff, for example. With some of our Parkinson patients, we have been monitoring them for 2 years now. So it is in patients' home, but of course, taking it to another level where it is your, fire smoke detector in each home. I think this is a vision where we want to move. In every home, there is something that is continuously monitoring the health. And I tell my students, I imagine that the future, those devices will be a platform like we have the App Store for the iPhone. You can write applications, develop things to check on grandma when she's taking her medications. But let me go back to what else can we do and what we are doing now. So one of the things, of course, everyone is talking about generative AI and ChatGPT. So we talk a lot about generating text or images, but how about generating health data, medical data? So one of the things that we are looking at is, can we generate from simple, cheap type of medical data, such as the pulsing that we all get from wrist devices, or I showed you we get breathing. Can we, from that, generate your EEG, for example, from your breathing? So or from EEG, generate fMRI data so that we can get some initial understanding of a condition before sending patients to more expensive diagnostic tests.
So this is somebody, maybe this Andrew can help you figure out the financial model for this. Is this something that you envision that is covered by insurance companies, or is this sort of like a Whoop or an Oura Ring that people just elect on their own?
So currently we are looking really at the science. Can we generate that data? Because that synthetic data will be used in two ways. Would be used to train machine learning models, because health data, of course, is very expensive and hard to obtain. And also it will be patient-specific in different mode. So for the the business part of it, I'm just going as follows your advice. Go to Andrew, whose company is just on the same floor as my company in the same building, and just ask him how to do that.
Sangeeta, I thought that the visual you had on the convergence that's happening in engineering and science here at MIT was really compelling. Can you talk about what's on the horizon with regards to this type of convergence and other ways that convergence we can be really looking forward to having an impact? And that was also touched along before, was saying it's not just discipline, it's really coming together on these subjects.
Yeah, thanks for that question. I think, as I mentioned, I'm trained as a physician as well as an engineer. And the way I see it, every major medical challenge will really benefit from this kind of convergent thinking. There are a whole world of inventions that are coming. A concrete example that we're really excited about is antibiotic resistance. So this is, of course, a big problem, and it comes in part from antibiotic overuse. And that happens because physicians, when they encounter a patient that might have a bacterial infection, don't have enough information in the moment. And so what do? You prescribe antibiotics. So one of the versions of the technology that I showed you, the breathalyzer, that we're working on allows, we hope, doctors who are taking care of pediatric patients. So kid comes in, we've all had this shortness of breath, they have pneumonia. Is it viral or bacterial? So the breathalyzer would allow you to just make that cut and decide in the moment, do I have to put this patient on antibiotics? And the use case that we're developing is for pediatric pneumonia in low and middle income countries, where in fact you often only have one touch point with the patient. So that's an example. I think there's many more in neuroscience and aging and infectious disease, other infectious diseases.
So many of you talked this, I'm going to open it up to everyone now. So many of you talked about how you're taking this idea from the lab and turning it into a company that can really bring its impact out into the world. Can you talk about sort of what the role of MIT has been in helping that along, the sort of the support and the encouragement that MIT has given along that road? And then bonus points because Dean Anantha and I are on the board of the Engine, and so compliments to the Engine are also welcome. Do you want to start?
Yeah, I feel like I have to. Our company was one of the first 7 that was funded by the Engine. In fact, my co-founder made a pitch to the Engine put out this call, if you're interested in interacting with us, let us know. Before they were founded, before they had a building, this was in maybe the end of 2016. And my co-founder said, yeah, we should apply for this thing. I was like, what are you talking about? I was not paying attention. I didn't know what the Engine was. I wasn't paying attention. So he fills out this form, and we hear from Reed from the Engine 3 months later, hey, I want to talk to you guys. I was like, about what? And so we talked to them and met with them, and they were tremendously supportive early on. But it hasn't just been that. We were in a program called the I-Corps. We were in the MIT Venture Mentoring Service. My postdoc, Paulo, who became the CEO of the company, had this Translational Fellows postdoc where they actually would pay for 1 day a week to allow you to pursue, independently look at, commercially related things, just with the realization that many postdocs are not going into academia. Many of them are looking to start a company or do something else, and so MIT was facilitating this. We took advantage of, there are a lot of things out there. In fact, maybe there's too much, and it's almost overwhelming how many resources there are out there. But if you can navigate it, it can be a huge accelerator, really for your students, for the students and postdocs who are looking to get into these areas.
So it's a huge benefit and strength of MIT that there are so many opportunities to get these ideas from the lab out in there, and there's a lot of support for it. Does anyone else want to talk about forming a company here?
Well, one of the crown jewels of MIT, certainly the Engine has done a remarkable job, but in addition to the Engine and prior to the Engine, and part of the reason for the Engine is one of the crown jewels of MIT is the Technology Licensing Office. I mean, many universities, I think all universities at this point, have a TLO, but MIT really blazed a trail in thinking about technology licensing in a very sophisticated and productive way. And so not from a profit center perspective, but rather from facilitating taking theory into practice. So I couldn't agree more with Pablo that we have to support basic science, because without basic science, you don't get all of the other stuff. But if you have the basic science, in order to get the other stuff, you need a mechanism to take that theory into practice, and the TLO does an incredible job of being able to do that.
Can you explain what the TLO does for the audience?
Sure. So the Technology Licensing Office basically files patents for discoveries that are occurring at MIT, and then they take those patents and license them to commercial entities, companies. And so all of the companies that you've heard about today, at some point or another, they interact with the TLO. And so their job is really to facilitate that translation from theory into practice. And MIT, not surprisingly, has been a leader in technology licensing. And to give you just one example, obviously, the life sciences has been a major beneficiary of technology licensing. But in the case of fusion, Commonwealth Fusion Systems was based on a very unique set of technology licensing agreements that allowed for-profit and non-profit entities to work together, hand in hand, and to deal with all the inherent conflicts of interest. So that's something that we don't really think about, but I think it's an incredibly important part of the ecosystem, and so they deserve a lot of credit. MIT's success and the Engine success really comes from that technology licensing over several decades.
That's great to hear, and the nonprofit for-profit collaboration is always tricky. Does anyone else want to add about starting companies?
Sure.
I think one of the things that's made it, particularly in my case, very much easier, and also like why we have a company in healthcare in particular. Like when we started, it was like we were thinking, oh, like a technology that we see people through walls, and like we can get everything from radio signals, like the Force in Star Wars, basically. But basically, MIT is a very, very collaborative environment. The ability to really work with people who are actually medical doctors at MIT, although we don't have med school, but we have many medical doctors even in our department, in ECS. We just cross the road, and just there is the Broad Institute, the COG, the Whitehead, all of these amazing resources and colleagues that we can just exchange ideas with. So that, I think, at least in my case, helped a lot. The other one is the students. I can't tell, I mean, I'm sure all of my colleagues here will agree with me that without the students, nothing would happen, nothing would be possible. Amazing, amazing, brilliant minds.
Chinwe, you were going to add?
Sure, yeah, I would say it's about the kind of the mentality of MIT community here, right? Doing a startup, it's just a norm, right? Everybody's doing startups. What a big deal, just go do it, right? Fail 3 times, the 4th time you'll learn how to do it. Right? The key thing MIT allows is it allows us to fail gracefully, right? Actually, I didn't appreciate this privilege we had here, right? In many parts of the world we visit, they literally ask, how do you guys do this, right? We do not have the chance to fail gracefully. I think we have the privilege to do so.
These are great things that we're hearing about, the secret ingredients of MIT that help it to be so successful. And what are, from your perspectives, what are some of the next big ideas on the horizon, and also any advice for President Kornbluth? And I'll start with you. Yeah.
Oh my goodness. Well, you're asking someone who comes from the world of nuclear, so I'm going to say, wow, climate change. Climate change is a big one. And here at MIT, we've put together a really exciting action plan for the decade, which is, yes, focusing on our students. We're thinking about education for climate change. It's absolutely focusing on the systems and working with society to do this. So we absolutely have a policy working group that's reimagining all of this. And these are just some of the pieces, I think, that have to come together for really fostering innovation, because we are going to have to pull from every discipline, from every department. We're going to have to inspire people through art and music to think about the planet and think about the health of the planet. But at the same time, we're going to have to be combining life sciences with computing and using that to connect back to the climate in really inventive ways that we probably haven't even thought of yet. So I would say, yeah, let's keep the imagination going when it comes to addressing climate change.
Climate change and keep the curiosity going. Sangeeta, what do you think?
Yeah, I was going to say, I think that it's an important part of our future that we are more inclusive than we have been historically. I showed you the plot of 130 startup companies out of the one building alone. What we discovered is there actually could have been 40 more.
Wow.
And that women at MIT were underfounding companies in the life sciences. And it's not just here. When we discovered that, we looked around the world, and it turns out to be, broadly true. And there's all kinds of reasons for that. But I think that if we really are going to meet the future, we need to make sure that we get all the minds at the table. And I know, Sally, that's something that's really important to you. So I'm excited about working with you on that.
That's great to hear. Pablo, what do you think?
I think that something that is in the horizon, and that it's also, it's even in the news, is quantum. A lot of the technology that we have nowadays stems from what we call the first quantum revolution, when basically transistors, and when we learn the basic properties of matter, but they were of the simple type that I had in my slide. Many people think that there's going to be a second quantum revolution, which harness at a much deeper level the complexity of quantum physics, new materials, and new technologies. And that is something that it's still very early stage. Requires a lot of basic research, but would much more dramatically impact the type of things that we can do. And not just in terms of materials, but sensors, even healthcare, all kinds of things that we probably don't even know yet. Because usually, if you can see it already, it means you understand it fully. It is when you start exploring things that you really don't understand very well that then something happens that you didn't even know that was so good and that could change the world in such a fashion. So I think that that's one of the things that I see in the horizon, and I think that it's important to keep in mind.
Andrew, do you want to add to that?
Well, so, asking me to give advice to President Kornbluth is a bit like asking the local tennis pro to give advice to Roger Federer or Rafael Nadal. So I hesitate to do that. But if I had to come up with something, and as an economist, I'm happy to opine, I think it's the think big. Think big, because we are now at an inflection point in society in terms of dealing with some very difficult challenges. And if we don't deal with them successfully, there won't be any future generations. And so that means that now is the time to act, and we have the opportunity to deal with a number of things, including antibiotic resistance and healthcare issues and climate change. I think that MIT is the perfect place where we are poised to have that impact, but we need to be able to think big and spend big, and this is the time to do it.
So investing, keep on investing. And I think that's one of the things that's been remarkable about MIT in the, 15 or so years that I've been involved here, is that the amount of investment and the willingness to take risks, the allowing people to fail gracefully, and sort of encouragement of that, the striving towards inclusiveness. It's a lot better than it has been, but there's definitely more to go. And this sort of eye towards the future is just some of the really special alchemy that you all have represented so well for us here today on this very, very special day in MIT's history. And given my role beyond MIT, I want to close with a little context of that this institution is not just in Boston and Cambridge, but it's also of Boston and Cambridge. And this beautiful view that those of us in the room have, those at home can use your imagination. There's this stunning view of the Charles River that flows through Boston and Cambridge and beyond. There's really something in the special in the water here, and Sangeeta's slide showed just a small touch of that, with the number of organizations and companies and bright ideas that come from that. And this is one of those just remarkable places where the impact is so great. And the people that come here to do their life's work to make the world a better place are not just choosing MIT, they're choosing to build their lives here in this region. And so I hope that you continue to think and support not only these great ideas, but remember the connection that you have. You're solving and thinking of problems on a global scale, and the future is truly being built here in an exciting way that you just don't see other places doing. And so connecting that and letting Boston and Cambridge be your lab and be the place where we figure out transportation. You guys have had these driverless cars banging around the seaport for years now, and to these companies that are starting up. And your fellow economist, Larry Summers, have said if you were to drop a pin from where we're sitting right now and draw a circle, 10-mile radius, there's more life science talent here than anywhere else on the planet. It's not an accident that MIT is part of it. So thank you all for sharing your dreams, your visions, and this beautiful future that you're imagining and building with all of us today. Congratulations to all of you on being part of this really historic moment in this very historic and meaningful institution. And thank you, Sally. We're so excited and all cheering. Your success is all of our success. So we're all here rooting for you. Thank you all. You were wonderful. You crushed it. Your presentation was very good.
Thank you, Linda, for doing such a brilliant job with moderating this discussion, and I found this really inspiring and engaging. So let's give another round of applause for Linda. And I'd like to also thank our truly remarkable faculty members who participated today. So another round of applause. And thank you all for joining us today for this discussion. And finally, President Kornbluth, once again, congratulations as we celebrate your inauguration as the 18th president of MIT. Thank you.